Welcome back. Our next session will be on Haskell with Kubernetes together, and it will be given by Mateusz. Please welcome Mateusz.
Hello. So yes, I assume you can see my screen now. So hello. So I'll be talking about performance for Haskell microservices on Kubernetes. There is a repo for this talk, and MH3 was smashed on Haskell. The shortest things I want to talk is that based on how you configure your microservice in Haskell, you can get either a throughput of 77 requests or 3,500 for the same container, which is quite interesting. I'm a Haskell engineer at Habito. We deploy our Haskell microservices to a Kubernetes cluster. And if you want to see how to build a nice Haskell Docker containers, check mini repo by Lunaris. It's really nice. It uses Bazel to build them. I will show and tell rudimentary performance tests for Haskell on Kubernetes. At the end, I want you to understand that hardware topology counts. It really matters for your deployments. Even a sketchy performance test helps. Setting up requests and limits on Kubernetes is a must. You really should do it. And threaded and not threaded GHC runtime are both fine. You should choose between both of them, but -n setting is not. I will also show you how to pin down GHC processes to the processor, and it's really nice. GHC really likes to be pinned to one processor. So the plan is, first we'll talk about empiricism and rationalism in reasoning about performance. Then we run a Haskell microservice versus a Node.js microservice on Minikube. Then I'll talk about Haskell runtime on Kubernetes and like on a computer how it works, and show and tell Haskell, Kubernetes, and Docker's performances. We'll do more of them. And then we'll fold it up to see what works, what doesn't. So at the roots of our problem is a very old fold, which was thought in ancient Greece. And the question is between rationalism and empiricism. We like to mess those two up. We're saying, yes, I'm a rational person, I believe in science and so on. But the idea is very different at its roots. The empiricism comes from the Heraclitean idea. Heraclitus is sometimes called proto-empiricism, that the only constant is change. The world changes, so you have to check how it is in order to know anything. Yeah, you have to check with your eyes. You have inductive knowledge. It's not very good, but it's the only one you have. And the rationalism comes from Parmenides, and he says that change is an illusion, and world as the object of knowledge is eternal. So the idea here is that the world, in order to be known, something can't change, because if it can't change, your predicates will change. So Platon, who wanted to get these two together, said that if the world is not a rational domain, then we know nothing. Thus the world is rational. Yeah, and a lot of stuff that was invented by him was made just to fit in with that assumption that the world is rational. Yeah, you've got the demiurge, you've got ideas, and the demiurge grants that the world is somehow obeys the ideas, and thus you can know about the world because the object of knowledge actually doesn't change. So we could define a rational domain as a domain which has one complete description. You've got a description, and you can reason about it. You can do some of it in math, yes? So the question is performance a rational domain? And I think a lot of people think it is. So in performance, we've got all these ideas how to describe it, yes? We've got rationalism, which is like efficiency in annotation, which doesn't even need a programming language, yes? Then you've got counting operations. For counting operations on a processor, you give an idea of your processor. You don't exactly have to have an implementation working. And then micro-benchmarking tinkering, this is what we'll do today, end-to-end performance testing, and finally production monitoring, a lot more on the empiricism side. Yeah, you have to run it on actual computer to micro-benchmark, and you have to have actually something in production in order to monitor production. So performance is a rational domain if the world preserves ordering moving left to the right, and this ordering is maintained on composition. This is what we would love to, yes? Because if performance is a rational domain, then you can be reasonable about performance, which means that if you use a good compiler and performance libraries, you do not have to measure your system because it works, yeah? I've got the best algorithm, I got very good libraries, and in Haskell, we've got very, very efficient libraries, then everything should work. A lot of programs, I think, assume that, as well as like to cite Donald Knuth saying premature optimization is the root of all evil. I think it's not that obvious when you look on the side of the production and on the side algorithms. Yeah, when you move to the side of the empiricism, things stop being obvious. So I want to show you that it's not that easy with performance on a modern computer. What we will do, we will run 2 benchmarks. The benchmarks iterate 1,000 times, 10,000 times, and they run a merge sort and insertion sort on a vector of 108. And the interesting thing is merge is the better algorithm, and insertion is thought of not being very good. It's nice on small arrays, but it has the problem of having a quadratic time in annotation. The funny thing is, like, insertion is faster. Yes, this is something that we could think. It's not a large vector, but it has also a lot more instructions. So if you measured instructions on your computer, actually the merge should win, merge sort. But what happens is the instructions per cycle differ. So the merge sort is waiting much more in the front end for instructions to be fetched from the instruction cache of the computer, and is waiting also for the data cache a lot more. It is also doing a lot of more branch misses. So what we get as an image is something like that. We've got insert on size 50, and it's like what you could expect. Yes, the insertion has less operations and is faster, but it can be also faster even for 150 elements on indate vector, while having much more operations because of the utilization of system cache, of good processor cache. It falls off at about 200, and not by a large margin. So when you change the description level from annotation to operation count to time, the ordering is not at all preserved, it changes. So what about the preservation over composition? Is actually a fun one. If you change the type from int8 to int64, this one is run using criterion, then insert is faster than merge on int8 for size 100. It is slower for int64, but what happens is actually insertion sort is slower on integer 64 than on int8, and merge sort becomes faster. And all these tests were done on worst case, which is reverse sorted order. So I would say that performance is not a rational domain, it's full postmodern. Yeah, postmodern means there are many different descriptions with different true functions. You ask, oh, is it faster? And depends on this description. Which one do we use? Yeah, do we describe like annotation or operation code on micro-benchmarking? It is a known fact in algorithm design. This is why we've got catch-up previous algorithm locality, introspective sort. We've got models of computation that include cache lookups for algorithms. And it has been talked about in the dev community. In the game programming and C++, it's called data-oriented design when you care about your cache utilization. And there is the idea of mechanical sympathy in Java community. If you get interested in this, these are both good reads. So at the roots of computing, and it's pretty funny when we think about mathematics, is actually hardware. Yes, and the first hardware came not long after we started to domesticate animals. So domestication of an ox came about 15,000 years ago. And you know, oxes are like 2 meters large, they're large animals. And we first started to make tokens to calculate things in order to calculate the storage of oil, olive oil, the storage of wheat, and the storage of actually to process also oxen. So the first tokens were created 10,000 years ago to store and process information on goods stored in warehouses by a community. And it's very hard to actually have a warehouse without data on the storage. Yes, things can vanish from it, they disappear. So with tokens, you can calculate the token, the oxens, the olive oils, and so on quite easily. And then later you can settle the deal while checking that your calculations agree with the count of the oxen. So when alphabet was coined, the aleph can be also called an ox head. Yeah, when you rotate it, it's actually a head of an ox, the letter A. And writing is a bit smaller than a token. Yet, even our first hard drives for IBM 350 did not get order of magnitude lower than writing. Yeah, we still have processing of information after nearly 10,000 years on the scale 10 to -3, like in scale of millimeters, which are visible. With the transistor, we managed to get in last 50 years from 10 micrometers to 7 nanometers. And now what happens with like software development, with web development, even, yes, modern writing spans 9 orders of magnitude. So even if you write simple web server or make a web page, you modify things from key presses, yeah, to atoms. And you can also add the submarine cables, which means that we make things which happen on the scale of 14 orders of magnitude. Yes, our cables are like 40,000 kilometers long. There's a lot of difference of a scale of what's happening. And how does it work in practice? So hardware has a topology. If you look at my computer, I'm using hardware locality ls topo2. You can see that I've got 6 cores. Each core has 2 threads. They've got instruction cache, data cache, L2 cache, F3 cache, and some memory. But these things are quite far away from each other in a way. So the access times differ not by 2 or 3 nanoseconds, but actually by order of magnitudes. For example, when we do an operation, as you could see, we were doing even like 3 operations. Yeah, I will move to here. As you can see, we can do about 3-4 operations per cycle, almost, or 1, depending what you do. So actually, you can do like, I would say 1/3, yeah, like 3 operations per cycle. Then when you want to access cache, it's half nanosecond, so it's 4/8 cycles. These are data from my processor. For L2 cache, it's 12 cycles. For L3 cache, it's 40. So it's actually now an order of magnitude. If the operation is like a typographic point and the L1 cache is a writing, then here we are back to operating token. But when you switch to DRAM, it's 100 nanoseconds at this time it can be. So it's basically the size of an ox. And once we move to things like context switch happens when operating system changes the process that is run on, for example, this thread. It has to take one, put another one there. And this can take 1,000 nanoseconds, which is basically herding oxens. So there are 3 orders of magnitude difference between L1 and DRAM, which is an ox versus aleph. And what it would give you is 100 frames per second versus 1 frame per second. Yes, 1,000 requests versus 10 requests per second, which is what you have seen in the first slide. So how bad does it get for us as Haskell developers? So what I do now is I will deploy a deployment of a non-limited node without any limit. It's the simplest deployment of a node you could do. On a Kubernetes cluster, I run locally with a Minikube. I wait for it to be running and for the old one to terminate. And now I'm going to run a very simple performance test on this. What I do is I use a tool called apib, which creates 200 clients, runs the test for 25 after warming up for 5 seconds, and waits 25 milliseconds between calls. I attack an endpoint which returns an array of 100 items. So it's a very processor-consuming thing to do in terms of parsing JSON and connecting to database and so on. And what I get is 2,500 requests per second. I could get maximally 10,000 from these tests, but it would be very hard to do. What I'll do now is I will deploy a rather simple deployment of Haskell microservice, which has the same functionality and which was built using the standard stack new template. It is running. It's optimized, if you like. And now we will smash Haskell. And we'll see how it performs. I'm actually quite interested because you don't know when you run it. I have videos, so the numbers will be different than I had when I ran it without streaming. But if you think about the Kubernetes cluster, you should think about something where everybody streams at the same time video. So it's not that different. As you see, our Haskell is an order of magnitude slower than Node, which is not very good, is it? And we're not limiting anything for it. It can do as many requests as it can. So if when I ran it previously, it was 3,000 requests for Node and 380 requests for vanilla. If you do a load test, which is more vain, it does maximally 2,000 requests, so you can compare latencies. It's not so bad, but still the 99th latency is 28 milliseconds versus 5. The Node is much, much faster. And the question is, why? Yes, why? We've got this Haskell, it's a compiled language, it should be fast. We've got Node, which is actually a very good technology, using a scripting language, but it has just-in-time compiler and very nice event loop. So there are many culprits. There is Kubernetes Docker hardware topology, Haskell runtime settings, but the worst offenders are GAC runtime settings. To the GAC runtime with -n setting, which comes standard with Stack New, and is quite often used by developers who think that they will get more threads, trust, more performance. The problem is that load balancing run threads on GAC capabilities by GAC runtime is fighting with load balancing Linux processes by completely fair scheduler. And in worst case, we get a full context switch instead of a green thread switch. Now, what does it all mean and how we can be sure that it works like that? So we can start collecting stats, which will run collection of context switches on our system, and we can smash Haskell again. At the same time, we'll be looking at HTOP. As you see, the processors, these are like all Haskell processes, all from the same deployment, and they're all jumping on different CPUs, changing CPUs all the time. Some of the processes are capabilities. They run our Haskell code. Other processes are foreign function interface threads. There can be garbage collectors, and we've got a lot of CPU usage for the fact that we can't even match Node in performance, yes? Which can run our cluster, by the way. So we'll be stowing that, and we're checking report. As it says, oh, it's interesting. But implementation threaded, it's had the biggest overhead when it comes to context switching. So what happens, you can see here, is we've got these processors. These processors are also capabilities on which our green threads will be run. Green threads will be created when we do asynchronous operations, or we create threads in the Haskell, in the language, yes? The runtime will run these on capabilities. These processes have to be put by operating systems on these threads. On one hand, we've got Haskell, which wants to be very optimal at putting these Haskell threads, these green threads, on capabilities. On the other hand, we've got the Linux completely fair scheduler, which wants to optimize putting these capabilities on the processors. And they basically compete with each other to be the best at their job, and they're good at their job. So they context switch a lot. Not because they are doing something bad, but because they are actually doing something that is needed. And we got a perfect storm spanning for orders of magnitude, yeah, which is like writing or herding a small herd of oxen, which is a lot of difference, which gives us a result of 1 order of magnitude of difference in the behavior of the system and a lot of CPU use, context switching, and it damages our Kubernetes node. So what we can do about it? The first thing we can do is we can set requests and limits on in Kubernetes on our deployment. Then we can match them with the runtime thread settings. So what we will do now is we will deploy a deployment with Haskell and to runtime. You can watch it being deployed. Yes, we've got it. So now we will smash this. So we're testing now a deployment. I will show it to you of Haskell, which has different settings. What it has 1 replica, but it has a request and limit set, which means that the scheduler, Linux scheduler, will preemptively give it some place on different threads. And we also have a -N2 setting for our deployment, which means that we'll use only 2 capabilities. And we can actually say it that a lot less Haskell processes are created for the deployment. And it's actually faster. It's got 3,000 requests per second. So by setting requests and limits and setting appropriate runtime setting, we became a lot faster. How does it compare? So if we compare it against, I say these are from previous data. If we compare it against the previous deployment, we see that we are faster than Node. We are faster than Node. We are much faster than vanilla, just running Haskell without any requests, without limits, and with -N setting. We have actually very good load data latency. Latency on load, yeah, it's a lot better than it was. And it's a lot better than Node. But is it a fair comparison? It's not fair because we're using 2 threads and Node was limited. So if you want a fair comparison, we should run Node.js add 2 replicas. And this is what we'll do. I'll deploy deployments to replicas. So they are running, and we can smash Node.js. So now we're using the load balancer from Minikube to attack both node pods at the same time. As you can see, for 2 threads, we get much better performance on Node than we get with -N2 settings on Haskell. The requests, yeah, it served much more requests at a better average latency, and all the other latencies were also much better. So what we can do, we can try to change the attitude, and instead of trying to make our Haskell deployment bigger, we can try to make it faster and compare. Yes, so we'll deploy a deployment of Haskell and 1 with 2 replicas, limited to 1 request and 1 limit CPU on a replica. So yeah, they are running, so we can smash it. So as you see, we're not getting much better than Node now. We're not getting any better, in fact. So in order to match throughput, we can also try, and it's our last idea to be faster, is to run a non-threaded runtime. Let's see if we deployed anything. So the cool thing about non-threaded runtime, which is running now, the old one is not clear, is that we've got only 2 processes, system processes, for 2 pods deployed, which means that it should minimize context switching of a deployment. Yes, now let's smash Haskell. So we're smashing it again, and what we want to get better throughput than Node. And I think we're getting it. The threaded, yeah, we'll see results. So we had more requests per second, and we had average latency also using 2 CPUs from our cluster. What we can see in this is that the non-threaded runtime has the largest throughput on a very large load. But if we compare an easier test, which is easier on the node, which has only 2,000 requests, then actually the end-to-end minutes n settings on Haskell show that they are quite interesting and should be considered. But you have to test things like that with your own deployment and with a custom test. But yes, Haskell can be better than Node, which is a good thing, isn't it? And this is not all we can do. If we want to deploy things and for them to be performant on Kubernetes, we can go with what we have now, which means basically that we preemptively put some time of operation. Yeah, everything is in the GitHub repo. It will give the time on the different threads, but we can pin a process to a thread. We can do even more. We can isolate a thread so that the operating system does not work on it, does not schedule things on it. And then we can put a process on this thread using a Docker containerization. And this is what we'll be testing now. What's more, you can set up your Kubernetes with static CPU manager, and this will be done automatically for you. So how to do that? What you do, you run a Docker, yes, and we'll do N1. We'll pin a threaded GAC runtime, and then we will smash it. So what happens now? I had 2 threads which are isolated on this computer, 11th and the 12th thread, and on the 12th now a Haskell process is run. So our server runs only on this system thread, which you can say it's here. it's a bit of a cheating because it actually has the access to the cache of the disabled thread. Yes, this cache will not be used by other process. And we've got 3,200 requests per second on one process on a single CPU, which is larger than we had from a vanilla node. What's more, if we run the same what I want to do now is I want to show you for comparison what happens if we run the same process limited to CPUs but not pinned. So we give it one CPU but it's not pinned, yes? And now we will smash it. So this is the same deployment run on a Docker, and it's not pinned to a processor. And as we see, it's much slower. In fact, when you accumulate data, you get a very, very strange view. The first thing is that the node, when it is pinned, yes, it has larger throughput. Also the non-threaded, but it hasn't got much larger throughput than it had when it's not pinned. And when it comes to non-pinned deployments on one CPU using only Docker, but it's equivalent to using Kubernetes, the best thing you can do is for throughput is non-threaded Haskell deployment. But once you pin, the N1 is much both faster when it comes to latency and has more throughput, as you can see in the latency stats here. The node is actually quite competitive, but not against a pinned -N1 Haskell deployment, which is crazily fast. So let's fold it. As I said, hardware topology counts. It counts where do you put your deployment on a machine, how do you set it up. If it's got preemptive scheduling and so on. Even the sketchy performance tests help. These performance tests that I run, they are not very good. The good thing about this tool is that it's very fast, it's easy to set up, it's very easy to test different scenarios, but it can't, for example, test caching because you only have one endpoint you can attack, so it will be always cached if you use caching. You cannot change how it changes with random requests. Yes. The other thing is it doesn't allow you to schedule clients appearing at a certain time. You always have a certain amount of clients which make a request after they finish after a certain amount of milliseconds. It's very good if you want to test the web server that clients connect to, because they will stutter when you stutter. Yeah. When web users connect to, when browsers connect to you, but it's pretty bad if you want to check processing of streams that will always arrive at the same time with the same amount of data. You should set up requests and limits on Kubernetes, because otherwise your deployments will affect each other. As you've seen, like some processes will evict your other processes and we make them context switch. If you give them time in advance by request and you limit them, you will make them affect other processes less, and you will guarantee some processor time for them. Threaded and non-threaded JC runtimes are both fine. They're interesting because like on on small loads, the threaded runtime will give you better behavior. On large loads, non-threaded is a good thing. It's more efficient, basically. And pinning down JC processes to the processor is nice, indeed. I think it's lovely. And more is like that. You should set up your JC runtime together with your Kubernetes limits and requests, and do set them up. Really do. Otherwise, you will have a cluster in the bad shape. Context switches in Haskell runtimes are costly. And you might even consider a non-threaded runtime because of that. The non-threaded runtime has two drawbacks. The first thing is blocking FFI, which causes the other one to be fast, the other one is a limit of 1000 connections. The world does not make any sense and does not care about your arguments, so test stuff. And please make sure to turn on your compile options, optimizations. That's all. Thanks.
Thanks, Mateusz. It's very helpful to learn about how Haskell and Kubernetes can work well together. You can find Mateusz answering some questions live in the sessions area. We'll take a short break now and begin our next session at 25 minutes past the hour.